let's take a look at the half-life of lithium-4. Now, if you need to remember what half-life is. Half-life is the amount of time that it takes half of the material to radioactively decay into another material. We did a graph up here with carbon-14, which had a half-life of 5,730 years. That meant that after 5,730 years, half the carbon-14 was gone. Then after another 5,730 years, another half of what was left was gone. So in this graph, we graphed the percentage of carbon-14 remaining. It started at 100% after 5,730 years. Half of it was gone. Then after 11,460, there was only 25% left. Then we kept going down along this exponential curve. All right, so the half-life of lithium-4 is really short, 9.1 times 10 to the minus 23 seconds. There's a little typo here. This is 10 to the minus 23. So that's really short. Sketch a graph of the amount of lithium-4 remaining if I start with 5.8 grams of it. Well, let's label our axes. Here we have the amount of lithium-4. We start off with 5.8 grams of it. That's 100%. And then that will be 50%, or 2.9 grams. There will be 0. Now we can think of these as this is 100%. This is 50%. Down here, of course, this is 0%. Now we need to scale our vertical axes, our time axes. And this will be 0 seconds. This will be, we can make this at 9.1 times 10 to the minus 23. Then this will be twice that, or 18.2 times 10 to the minus 23 seconds. And then, oh, I made it 3. I shouldn't have made it 3. I should have only made it 2, shouldn't have I? Right here. 18.2 times 10 to the minus 23 seconds. Then this will be what? 27.3. And I shouldn't have put time right here. Time should have went way down here. And then the next one will be 36.4. And then the next one will be 45.5. So you can see this is not a lot of time it decays. So we start off with our 5.8 grams at the start. Then at 9.1 seconds, we're down to 2.9 grams, right? Half of it's gone. Then after another 9.1 times 10 to 23, half of the 2.9 is gone. Well, half of the 2.9 will be right there, whatever half of 2.9 is. Half of 2.9 is 1.45. Then half of that will be gone. And we can just do this visually now. Right, half of that is there, then half of that is here. And then eventually it gets smaller and smaller until there's almost nothing left. We can connect these up with a nice curve, nice exponential curve here. I missed my last point. And it will not go, it will eventually go to 0. And that's our graph. Now, if you look at this graph, it's essentially the same as this graph here. It has the exact same shape. All we did was scale our vertical axes and our horizontal axes different. See, instead of 100%, we have 5.8, and we have that for our half-life. Now, we need to talk about the formula for this. Now, if you remember from before, our formula our percent left is equal to 2 raised to the power of negative x divided by the half-life. So in this case, our percent left, and I'm going to erase my time here. For lithium-4, our percent left is equal to 2 times negative x to the power over 9.1 times 10 to the power of negative 23. That's our percentage left. But we don't have percentage left. We have our grams left. So our amount left is equal to 5.8 times our percentage, 2 raised to the negative x divided by 9.1 times 10 to the minus 23. So our amount left is our starting amount right there. That's our starting amount. Times our percent left. Now I can go and I can graph this on Desmos. And we can see what it looks like. Now, this is going to get pretty narrow, but it should work. We just need to be able to scale things quickly. So I'm going to go to Desmos. I'm going to see if I can remember the whole thing. So y equals 5.8 times 2 to the power of, I'm going to put brackets around, negative x divided by, what was it, 9.1 times 10 to the power of negative 23. Yep, that's what it's supposed to look like. It looks like a square. That's because it's going very, very steeply down. And I need to be able to scale my graph, just the horizontal part of my graph. So I'm going to scale this. You can see how I'm just grabbing the horizontal and scaling the horizontal out. I can't even see it. So keep going. See, look, we're 10 to the minus 8s, 10 to the minus 9s. We're going to get to 10 to the minus 23s. Keep going. It's much easier on, this is much easier on the iPad than it is on a phone. Almost there. Ah, there we go. There's our graph. You can see we start out with 5.8 grams, and you can see our scaling. There's 5 times 10 to the minus 23. So if I went x equals 9.1 times 10 to the minus 23, there'd be 2.9 grams left, 50%. After one half-life, 50% of the material is left. All right, so let's go back and let's finish this off. So you can see the percent left is equal to 2 to the power of negative x divided by the half-life. The amount left is equal to the start amount times the percent left. Now, lithium-4 decay. Lithium-4 looks like this. It's got 4 and 3. Lithium has 3 protons, 1 neutron. Lithium-4 decays by proton emission. So it just ejects a proton out. So a proton will be 1, 1. And what are we left with after we eject a proton out? Well, we're left with 3 items in the nucleus, and 2 of them are protons, which means we're left with helium. So lithium-4 decays into helium-3. Now, what happens to the last atom? The last atom, so the last lithium-4 atom there is a 50-50 chance it decays within one half-life. Now this is random, so that last atom could still be lithium-4 for a really long time. Well, not for a really long time because the half-life is very short for lithium-4. But it could stay around for a few half-lives as lithium-4 and just not decay. Because there's a 50-50 chance that it will decay within the half-life. So the last atom of lithium-4 will have a 50-50 chance of decaying within one half-life that it's left. So it may stick around for a few half-lives before it finally does decay. It may stick around for 1,000,000 half-lives, but that would be a very rare instance. So that's what half-lives are. The half-life is the amount of time it takes for half of a radioactive substance to decay into another radioactive substance. If you remember, why do they decay? Is they decay to get to a stable nucleus arrangement. Lithium-4 is not a stable nucleus arrangement. Having 3 protons and 1 neutron is not stable. Very much not stable. So it decays so it can get to a stable nucleus arrangement. And helium-3 is probably more stable. I'm not sure how stable it is. But it'll keep decaying until it finds one. Right? So remember this formula, how to make this formula? And remember these exponential graphs of half-lives.